Hey everyone, and welcome. Today, we're going to break down a truly elegant algorithm that honestly powers so much of our digital world, often without us even realizing it. It's called Dijkstra's algorithm. And yeah, it's the magic behind your GPS, but its story is just as cool as what it does. So let's start with a question we've all asked ourselves, right? You pop a destination into Google Maps or your car's GPS. How on earth does it look at this massive, tangled web of roads and, in just a blink, find the absolute best route? Well, the answer lies in solving a really fundamental problem about networks. And the story behind this is just amazing. We're talking 1956. A young Dutch computer scientist, Dijkstra, is out shopping with his fiancée. They sit down for a coffee, and in about 20 minutes, get this, without even a pen or paper, he comes up with the entire algorithm right there in his head. An idea born on a cafe patio that now runs billions of times a day. Incredible. All right, so here's our game plan to really get this. We'll start with the core problem it solves, then we'll look at how the algorithm actually works, we'll walk through a step-by-step example, connect it all to the Google Maps you use every day, and then wrap up with a final thought. Okay, first things first. We've got to understand the exact problem Dijkstra was trying to solve, and it's a small difference in words, but it's a huge difference in concept. You see, finding the fastest path is a total nightmare. It depends on live traffic, accidents, construction, things that change minute by minute. So to even begin to solve that, we simplify the problem. We first ask, what's the shortest path? This version looks at a fixed number for each road, like its distance. And that's the puzzle Dijkstra's algorithm was designed to master. To do this, we have to see the world like a computer does, as a graph. It's pretty simple, really. Every intersection is a dot, or a node. The roads that connect those dots are the lines, or edges. And every edge has a weight, which is just the cost to travel it. Let's say its distance. And the key rule is a smaller weight is always better. So how does the algorithm actually find the path with the smallest total weight? It's not magic. It's just a really, really clever strategy. The logic is actually beautiful. You start at your origin and you say its distance is 0. Every other spot on the map, its distance is infinity for now. Then you just follow this simple loop. Always pick the unvisited place with the smallest known distance from the start. From there, you look at its neighbors and ask, hey, is it shorter to get to you through the spot I'm at? If the answer is yes, you update its distance. And you just keep doing that over and over, always expanding from the closest point you're sure about. Now, to keep everything straight, the algorithm uses a couple of key tools. The first one is a distance array. You can just think of it like a scoreboard. It's a list that keeps track of the best, shortest distance we found so far from our starting point to every other point on the map. And the second tool, well, this is the secret sauce. It's called a priority queue. This isn't just any old to-do list. It's a special list that automatically keeps the node with the smallest distance right at the top. This makes sure that the very next place we check is always the most promising one, so we don't waste time going down a long, dead-end road. Okay, that's enough theory. Let's actually watch this algorithm do its thing. This is where it's all going to click. Our mission is to find the shortest path from node A all the way to node I. We're going to use colors to keep track of what's happening. Green means we found the absolute shortest path to that node. Blue means we're currently exploring it. And red means we haven't even looked at it yet. So we kick things off at our start, node A. Its distance is 0, and we color it green. Now we look at its direct neighbors. B is 2 units away, and C is 3 units away. They both get colored blue and added to our priority queue. Okay, so that priority queue tells us that B, with a distance of 2, is the closest node we haven't visited yet. So we lock it in, turn it green, and check out its neighbors. The path to D through B has a total cost of 2 plus 3, that's 5. And the path to E is 2 plus 4, which is 6. We add those new paths to our list. Now pay attention, because this is the aha moment. This is the whole magic of the algorithm. The next closest node on our list is C, at a distance of 3, so we visit it. Now look at its neighbor E. The path to get to E through C is 3 plus 1, which is 4. Wait a minute, our old path to E was 6. 4 is way better than 6. So, and this is the key, we update our scoreboard. We say, nope, the new best way to get to E is 4. This is what it's all about, constantly finding and recording better paths.
And from here, you can probably see the pattern, right? The algorithm just keeps doing this simple little dance. It grabs the closest blue node from the list, colors it green, checks its neighbors for any shortcuts, and updates the scoreboard if it finds one. Lather, rinse, repeat.
And after running through those steps until our destination, I, is finally colored green, we have our answer. We can trace it back and see the shortest path from A to I is through C, E, H, and G, for a grand total distance of 9. And we found it efficiently without having to check every crazy combination. So, that's a cool little puzzle, but how does this abstract idea power the real-time directions on your phone? Well, the trick is simple, but it's pure genius. Instead of using distance for the weight of each road, Google Maps uses estimated travel time. And, unlike our simple example, those weights are not fixed. They are constantly dynamically changing. Think about it. Your phone, and thousands of others, is anonymously reporting its speed back to Google. When the system sees a whole bunch of phones suddenly slow to a crawl on one stretch of highway, it knows there's a traffic jam. And instantly, the travel time wait for that piece of road shoots way up. The algorithm immediately reruns with the new, higher cost, finds a new best path that avoids that mess, and seamlessly reroutes you. It's happening constantly. Okay, let's zoom out for a second and just reflect on the power of what we've just seen. It's truly a testament to how fundamental ideas in computer science aren't just abstract theories in a textbook. They are living, believing code that actively shapes our world every single day. That simple, elegant idea that Dijkstra thought up in a cafe, it solves a problem of immense complexity with a rule so simple you can explain it in a few sentences. And that leaves us with a final thought to chew on. We've seen how something as massive as global navigation is built on the simple rule of always explore the closest next step. So what other complex systems in your life, maybe things like social networks or even biology, might also be running on a single, elegant rule hiding just beneath the surface? Thanks for tuning in.